So last time, we saw that we could actually test for type 1 Zeno. And the way we could test this was to see whether or not the gradient, dg dx transpose, points in the same direction as F2 and the opposite direction to F1. So if I have that, then I do have type 1 Zeno. And we came up with a little probe here to check whether or not this is indeed happening. So the first thing we do is we check LF1G negative and LF2G positive, where LFG was this thing we called the Lie derivative, which was simply just fancy speak for dg dx times, in this case, F1 of x. That's all that means. So this is the probe that checks whether or not sliding occurs. Today, I want to talk about what's called regularizations, which is code for, okay, let's say we have that. We have sliding. How do we compute how we slide? And it turns out that this is going to be very important when we move on to robotics, because this occurs quite a bit when you actually start running robotic navigation systems. So today's lecture is all about how do we actually slide along this surface. Well, let's actually try to be a little careful when we figure this out. So if I'm sliding here, what is characterizing that motion? Well, I know that g of x is equal to 0, which means that if I take the time derivative of g with respect to t, then it should be 0, because g is not going to change when I'm sliding, because I'm staying at g equal to 0. So one thing we need to do is say that dg dt is equal to 0. Well, let's see where that takes us. dg dt is equal to dg dx times x dot. So now, what is x dot along here? Well, what I'm going to postulate is that it's a combination of F2 and F1. In fact, let's say that it's equal to sigma 1 times F1 plus sigma 2 plus F2. So it's a convex combination of these two vector fields. So if I do that, I get, instead of x dot, I get this thing here, sigma 1 F1 plus sigma 2 F2. Well, since these are scalars, I can actually pull them out here, which means that I can write this expression that's a little bit messy looking, like sigma 1 times the Lie derivative of g along F1 plus sigma 2 times the Lie derivative of g along F2. So that's what the time derivative of g actually is. But I want that to be equal to 0. This needs to be equal to 0 because that was our condition. So if I put this thing equal to 0, then I can solve, for instance, for sigma 2, and I get this expression right here. So I know how sigma 2 is going to depend on sigma 1. Well, that's a good start. We also know that both sigmas need to be positive, because I'm not allowed to all of a sudden start flowing backwards. And they also should sum up to 1, because otherwise I can go super fast along this direction, which I typically don't want. I want it to respect the dynamics. So I have additional constraints here. The sigmas need to be positive, and they need to sum up to 1. Well, let's see how we can actually solve that. So let's go back to our old friend, the example. And again, this example looks like this, where, you know what, I'm sliding down with slope minus 1. Here's x and here's time. And when I hit the switching surface, I stay with x equal to 0 for the duration. Okay, what is the switching surface, first of all? Well, it's x equal to 0. So g of x is simply x equal to 0. Okay, let's compute some of these Lie derivatives. So LF1g is the derivative of g with respect to x. So the derivative of that with respect to x is simply 1. F1 is simply negative 1. So the Lie derivative is negative 1, which is one of the things we needed for Zeno. We needed, or for sliding, we needed this to be negative for type 1 Zeno to occur. That's the first. Well, let's do the same for F2. Sorry, this is an F2 right here. Apologize about that. LF2g, well, it's dg dx, which is equal to the derivative of that with respect to x, which is 1, and F2, which is plus 1, right? So I get 1 times 1, which is equal to 1. which is positive, which was the other condition for having type 1 xeno. So we know that we actually have type 1 xeno or sliding here. Okay, so now let's try figuring out what these sigmas should actually be. Well, we had a formula for sigma 2. It is equal to negative sigma 1, and then these two Lie derivatives divided by each other. Well, this was negative 1, and this was plus 1, so sigma 2 is simply equal to sigma 1. Rather simple, right? But what are they? Well, recall that they need to sum up to 1, which means that they both have to be a half. What this actually means then is that we can compute what the induced mode, the sliding mode, actually is. Well, I take sigma 1 times f1, which is half of f1, and then I take sigma 2 times f2, which is half of f2. Well, f1 is negative 1, f2 is plus 1, so I get negative 0.5 plus 0.5, and that's equal to 0. So I know that my induced mode in this case is x dot is equal to 0, which is exactly what we wanted. Because remember this picture that we've drawn over and over again. We want to start here, get down here, and then keep staying at 0. And the math turned out to work out in this case. Now, let's find the induced mode in general. I know that the general formula for sigma 2, and I want to point out that this is not a formula anyone in the right mind should memorize, but we should know where it comes from and be able to use it when we need to. But here is the general formula for the induced mode. Well, we also have that sigma 1 plus sigma 2 is equal to 1, which means that I can take sigma 2 here and plug it in, because this is what sigma 2 is. So now I have an expression on sigma 1. So if I solve that, I actually know what sigma 1 is. I encourage you to go through the math yourself. It's a little bit of a mouthful, but what it tells me is that I can compute sigma 1, and I can compute sigma 2 just as well. And if I now sum all of this up together, I get this expression inside the pink box here. And I recognize, again, this is a little bit of a mouthful, but what this tells me is exactly what the induced mode is. So I am going to put a sweetheart around this thing, not because it's particularly pretty, but because it's systematic, and it tells us how to actually find the sliding mode controller, or the induced mode, which means that we know exactly not only when type 1 xeno occurs, but how to progress beyond it. So let's figure it out. If I have, this is my hybrid system, and if this is a type 1 xeno hybrid automaton, how do I regularize it? What do I do to add this extra sliding mode? Well, this is what I do. And now let's parse this. Even though it looks a little bit like a mouthful, let's figure out what it means. So let's say I am here. G is positive, and all is well. Then, if G becomes 0 and the sliding condition is satisfied, then I move into what we just computed here, which is the induced mode. And again, it's a little bit of a mouthful, but we will see later on that in robotics we have no choice but to actually use this. So then I'm going to use this mode until, if G becomes positive, I jump back to F1. If G becomes negative, I jump to F2. And of course, we don't always have type 1 xeno. Some switches are nice. So if I simply end up with G negative, I jump directly from mode 1 to mode 2, and vice versa. So this is how you take a hybrid system and make it immune to the nauseous and bad effects of type 1 xeno. And the nice thing is that this is completely general, and we don't ever again have to worry about xeno. Type 1 xeno, type 2 xeno, we always have to worry about. Having said that, this actually brings me to the summary of this entire module on hybrid systems. So what do we have? We have models. We have very rich models, which are these hybrid automata models. We have something that we call stability awareness here. We're aware of the fact that just because the sub-modules or the sub-modes are stable themselves doesn't mean that the hybrid system is stable, and we need to be aware of it, test for it. We also have seen xeno as another awkward hybridization that occurs, or an awkward phenomenon that can occur when you go hybrid. We have two classes of Zeno. One, which is type 2, which is the bouncing ball. Infinitely many switches in finite, but not a 0 time. That's bad and scary, and we can't do anything about it except look out for it. But then we have type 1. And we now know not only how to check for it, but how to get around it using these things that I call regularizations, or the induced sliding mode. And with that, if I had, a confetti, I would toss it up into the air, because this ends the mathy part and the pre-robotics part, really, of this course. So what we're going to do in the next module is go back to robotics, apply all of our new and awesome tools, and see how we can unleash them to actually make mobile robots do cool things in the real world. Well done.